We want to return to our discussion of configurations and talk about noble gas notation.
So when we look at these electron configurations that we've talked about before, and we look at, say, standard notation for neon, magnesium, and aluminum, Ne, Mg, and Al, we can see one of the whole ideas that we talked about was that they just kind of keep building upon themselves. And so if we look at this, these are all close together, we can see that this group right here is all exactly the same. They're all common. And so when these configurations can get really long and onerous, we want to maybe save some time. And so what we're going to do is we're going to use what's called noble gas notation. And in noble gas notation, what we're going to do is we're going to show the previous noble gas, basically of the noble gas before that atom. We're going to put it in brackets, and then we're going to show the rest of the configuration. So for example, magnesium and aluminum, you would put Ne in brackets because we already have it labeled here. This is the electron configuration of Ne. So when we write this just brackets Ne, we're implying that that is what's there for magnesium. And then the only thing we focus on is what's different, right? What is different about magnesium from neon? And we can see that that's the part that's right there. Similarly for aluminum, we have the 3s2, 3p1, which is the only thing that's added on top of neon. But whenever we see that neon in brackets, that's everything packed away in there. We don't have to rewrite it out. Those are all full subshells. They're not in the valence, so we don't care about them as much. They're not going to be as relevant. Let's look at some examples then of coming up with noble gas notation. So I've got 4 atom types here, and I want their electron configuration in noble gas notation. This is actually the most common notation that we see used, just because it is much easier to use, much quicker to write than full standard notation. So I got Br, Kr, Mg, and Ca. If I want to approach this, the first thing I want to do is find what is the preceding noble gas. Hopefully you're convinced that the periodic table contains all information about electron configurations that we would ever need. And so whenever, similarly that we did before here, we want to turn to the periodic table and see where are we in relation to other atoms? Where is it going to be situated? And then once we know that, we can then just trace out what subshells are filled after that noble gas, because that's the only thing we need to actually specify in the noble gas configuration. So bromine is right here on the periodic table. So when I want to find the preceding noble gas, it's important. It's not the closest noble gas. Br is obviously right next to Kr, which is a noble gas. But we want to go to the preceding noble gas, which is going to be the noble gas of the period above where we are. So above bromine, that's going to be argon, Ar. So we know that it's going to start with Ar. Okay, so we're going to start with Ar. That's going to be put in brackets, and then we're going to just put in everything on top of that. So the question is basically what electrons would be added, where would they be added after all the ones that are the same to match argon? And we know that's going to line up with right here. So it's going to be 4, and it's going to be S, because we're in the S block. So we're in 4s, and we can just use our Aufbau ordering now. We know we're starting in 4s. And we can also say bromine is in the P block, and it's going to end with 4p and 1, 2, 3, 4, 5th column. So it's going to end with 4p5. We even know that much. So bromine, the noble gas configuration is Ar in brackets, right? That lines up with that right there. And then we have 4s2, 3d10. That corresponds to this right here. And then the 4p5. So you can see we fill up the S, we fill up the Ds, and then the 4p5 is what is open on the bromine. Kr, we want to find where's Kr on the periodic table. It's right here. If we think about Kr, it is a noble gas. So we don't need to, in this case, find the preceding noble gas. The electron configuration of noble gas is just Kr. You can just write it as Kr because we've decided we're all going to use these noble gases. Boom, just throw them in brackets. And we know we can use the periodic table to interpret what that means. Anybody can figure out what the part is contained within Kr. Mg is right here on the periodic table. So our preceding noble gas is going to be this Ne. So we know we're going to start with neon, Ne. And then the question is, well, neon is full. Where do we go after that? We're in period 3, and this is the S block, 1, 2, we get all the way to magnesium. So it's just going to be Ne with 3s2. So that's all we would have is that Ne3s2. Basically, we have all the same electrons as neon, and then the extra electrons are just 2 electrons in the 3s subshell. Ca, calcium, is right here. The preceding noble gas is argon. Okay, and then we can see after that is 4. Again, we're in the S block, 1, 2. So 4s2 for calcium is all we got. So argon in brackets, right? That matches up with that right there. And then the 4s2 is the stuff that has been added the extra electrons on top of what you had similar that matched argon.
Participation 622, question 4. Write the electron configuration for each of the following atoms in noble gas notation. It's carbon, aluminum, and titanium. Fourth question on participation 622 due Monday, June 22nd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, write the electron configuration for each of the following atoms in noble gas notation. It's carbon, aluminum, and titanium. You maybe have some information from other places on these atoms. You don't have to refigure everything out.
So one of the things about this noble gas notation is it really emphasizes the fact that atoms in a given column of the periodic table have the same number and type of valence electrons. So if we look at, for example, group 1A, they all have one valence electron, and that valence electron is all of them are in an S-type subshell. So they all have they would all kind of look the same from the perspective of a different atom. The only difference is the shell that those electron is in, right? 2, 3, 4, 5, 6, 7, whatever it is. But that just changes the size of the orbital, not the shape or the orientation of the orbital. And so that means they all have similar electron configurations. They all look the same. They're all going to do the same type of chemistry. So all atoms in a group have similar chemical properties because they all have similar electron configurations, specifically the type of valence, the type and number of valence electrons. So group 1A, remember the alkali metals, were all really reactive. They just have that one valence electron. So that's why they have, it's kind of just one thing to move around. They're going to really change that, be really easy to change that quite a bit. I do want to take a little bit of time just to point out that all the electron configurations that we've been talking about would be predicted electron configurations. There are examples, because of course there are, where there are exceptions. So silver, for example, we'd predict it to be krypton with 5s2-49. It's actually 5s1-4010. That comes from actual experiments. The reason why I'm telling you this is not because I want you to learn exceptions. Do not learn the exceptions. These are not useful. There are explanations for them, but you have to explain every single atom why it breaks these rules. You'll note if you go back and look at the names, they're all rules and principles, not laws. So laws can't be broken, but rules can and are broken. That's why they're called rules, because they are kind of guidances, but not always true. And you will note that these silver and lanthanum exceptions break the Aufbau principle. They violate the idea that you should always fill, right? You can see that in actuality, the 5s isn't full and 4d gets electrons. So that's the violation on silver. The reason why I'm telling you this is not to memorize them, but just if you poke around and try to do some practice, you can try to figure out the electron configuration for anything, and then you can just look them up to see if it matches. You just want to be careful because sometimes you'll see things that are a little weird. Most of them, there's a couple in the D block. Most of them are in the F block, where we, as you hopefully have noticed, have not been doing a whole lot of work in the F block on purpose, just because it gets a little dicey down there and gets a little confusing. There's a lot of exceptions. A lot of things get a little wonky when you start dealing with F-type electrons.
That's it. 4 questions on participation 622. You want to find all 4 of those questions, get them answered, and get those answers submitted over on Blackboard by Monday night. We got a Tuesday participation, Module 7 homework, periodic trends lab on Tuesday on campus, and then we'll do the exam on Thursday. Meet at 9 a.m. Like we've seen previously, we'll go to lab afterwards. We will not have a lab activity, a kind of conventional lab activity with pre-labs and stuff like that. We'll be doing the lab practical, where you will, like a little test kind of in lab. There'll be more information about it in tomorrow's set of videos. And then don't forget the lab technique presentation questionnaire, just picking a topic and a format. And if you want to present on campus, picking a time. And then we'll have lecture module 8 at the end of the week. If you have any questions about anything, let me know. Otherwise, the only thing that's left for this is the participation answers, which go live Monday night. Otherwise, enjoy the rest of your day. I'll see you later this week. Bye-bye.